Dear students, welcome back to my channel. In this class, let us discuss about your second chapter, electrostatic potential and capacitance. Okay, it brings you 8 marks. It is also an important chapter, just like the first chapter, electric charges and fields. Okay, see, they can frame that 8 marks like this. They can ask you one 1 mark question, one 2 mark question, and one 5 mark derivation. Otherwise, one 1 mark question, so one 2 mark question, and a numerical problem for 5 marks. Okay, na? See, the word potential is not new to you. I think you might have heard about gravitational potential in your class 11, isn't it? Okay. In general, what is the meaning of that word potential? Both the teachers and parents always used to say that, hey man, come on, do it. You have that potential to do. Like that, isn't it? See, that something to do needs an energy, isn't it? If we have energy, then we can do that work. So, whenever work is said to be done, some amount of energy has been sent. That is the actual meaning. Therefore, potential means it is the word which is something to do with work. Therefore, so we will define the word gravitational potential as the amount of work done in bringing a body of mass 1 kg from infinity to any point in the gravitational field. At which point we should know the value of gravitational potential? To that point we should bring a body of mass 1 kg from infinity. Okay na? Similarly, here in case of electrostatic potential, we just replace that mass with the charge. Okay na? See. First of all, let us consider unit positive source charge plus Q, which gives the direction of electric field outwards. This electric field will be outwards. It starts from the positive charge and end at infinity. At infinity, the value of electric field due to this positive charge becomes 0. Okay. Therefore, let us consider a point called infinity. At infinity, the electric field will be 0. Okay. Now, let us define the word electric potential. The word electric potential is denoted by capital V. Okay. How to define this electric potential now? Suppose I said already, this is the direction of electric field. For example, at some point P, at a distance of some small r, we have to know the value of electric potential of this source charge plus Q. It is the source charge. This is the charge under consideration. Okay, na? See, here at infinity, we have to consider a test charge. I will mark this as plus Q naught. It is a test charge. Test charge. We usually call it as unit positive test charge. Okay, fine. See, fine. Now, our intention is to know the value of electric potential at this point P. For that, what we should do is, we have to bring this unit positive test charge from infinity to this point against the field direction without any acceleration. When there is no acceleration means the force, other forces on that charge will be 0, just like that. See, the electric potential at a point in an electric field can be defined as the amount of work done in bringing a unit positive test charge from infinity to that point against the field direction. Why I am using that word against? What makes the difference if we move that charge along the direction of electric field? See, actually what happens? This is the source charge I have considered. This is the direction of electric field. Here is the positive charge, positive test charge, plus Q naught. See, we have to do this, or we have to bring this in order to, we have to push it in order to bring towards this plus Q. Otherwise, suppose if it is minus Q naught, then we need not to do anything. We need not to do anything because no work is required here. Because of force of attraction only, it will come towards this positive charge. Therefore, work done by us is 0. Here, everything is handled by this source charge, force of attraction, isn't it? Therefore, so in order to say that work, we have to take, if here is positive charge, we have to take the positive charge. If here is a negative charge, then we have to use negative charge. But people always used to take positive charge. Let's be positive. Okay. So actually this is the meaning. Otherwise, the concept of gravitational field and gravitational force says that suppose it is some reference point, reference level, just like ground level, ground. Here is an object. For example, a tennis ball. I have to move this ball from this point to this point. So no need to do the work, isn't it? Because simply if you drop this, it will fall. Work is done by the gravitational field or gravitational force. In the same way, if you take the negative charge here, we no need to do that work. So it will get attracted towards a positive charge due to electrical force. But in order to lift this ball from ground level to this level, we have to do the work against gravity. Against gravity, isn't it? That is acceleration due to gravity, which is always towards the center of the earth, pointing towards the center of the earth. Okay, fine. Like that. So therefore, I have used that word against the field direction. Let me repeat the definition for electric potential again. Electric potential at a point in an electric field is the amount of work done in bringing a unit positive test charge from infinity to that point against the electric field direction. Okay, now that is electric potential is given by, it is the work done divided by charge. Work done is W, charge is Q naught, therefore V is equal to W divided by Q naught. If Q naught is equal to plus 1 coulomb, then we say that V is equal to W, that is electric potential is the amount of work done or amount of energy spent in moving that unit positive test charge from infinity to that point. Okay, now, so this is the definition for electric potential. So I will repeat once again. Electric potential at a point in an electric field is the amount of work done in bringing a unit positive test charge from infinity to that point against the field direction. Okay. Now, what is the SI unit for this electric potential? SI unit. See, W means work done or energy. Therefore, joule. Q naught, charge. Therefore, joule per coulomb. Okay, na? Otherwise, we can also say this as volt. Volt is the SI unit of electric potential. What is the dimensional formula? Dimensional formula. For joule, we used to take m L square T power minus 2. For C power minus 1, what we used to take? A power minus 1, T power minus 1, isn't it? Because coulomb means current into time. Therefore, A power minus 1, T power minus 1, which gives us finally m L square T power minus 3 and A power minus 1. This is the dimensional formula for electric potential. Now, is it a scalar or vector? Please remember, since V is having two scalar quantities, it is also a scalar. Electric potential is a scalar physical quantity. Okay, fine. Next, one important 1 mark question will arise in your annual examination. What is that question means? Very important question. They used to ask like this. Define the SI unit of electric potential. Define the SI unit of electric potential. What is the SI unit of electric potential? Joule per coulomb or simply volt. Now we have to define that 1 volt. See, very simple. See, we know that V is equal to W divided by Q naught, isn't it? If W is equal to 1 joule and Q naught is equal to plus 1 coulomb, then V will be 1 volt. Okay, now when W is equal to 1 joule and Q naught is equal to plus 1 coulomb, then V is equal to 1 volt. Now you can able to define what is the how to define the SI unit of that electric potential. Electric potential at a point in an electric field is said to be 1 volt if 1 joule of work has to be done in order to bring plus 1 coulomb of charge. Otherwise, you need to positive test charge from infinity to that point against the field direction. Like that, you have to define. See, I will repeat once again. Electric potential at a point in an electric field is said to be 1 volt if 1 joule of work has to be done in order to bring plus 1 coulomb of charge from infinity to that point against the field direction. Like that, we usually define the SI unit of electric potential. Okay, now see. So, according to the convention, the electric potential due to positive charge has to be taken as positive potential, and the electric potential due to a negative charge has to be taken as a negative potential. It comes under note. Potential due to, electric potential due to a positive charge is taken as positive. Similarly, potential due to a negative charge is taken as negative. Please remember. Similarly, I would like to give you one more point. The electric potential of Earth is taken as 0. Please remember. The electric potential of Earth is taken as 0 volt. Earthing, grounding makes what? 0 potential. Why, sir? Why the electric potential of Earth has to be taken as 0? Actually, we have not taken here. We have considered it as 0 because, see, our Earth is a big spherical reservoir having a radius of approximately 6,400 kilometers. In this huge reservoir, if we add some charge or if we remove some charge, then it makes no difference to its electrical status. Therefore, so even though we are adding the charges, even though we are removing the charges from the Earth, we often take the electric potential of our earth as a big zero. Please remember this. Okay, fine. Next. Among positive charge, positive potential, negative potential and zero potential, whose magnitude is more? I mean, among plus V, minus V and zero, which is more? Positive potential is more or negative potential is more or zero potential is more? I will tell you a small thing to understand this. See, take one positive source charge. The direction of electric field will be like this, which is outwards. Our overall intention in potential case is to bring a unit positive test charge from infinity to any point. Okay, na? See here. Similarly, I will take a negative charge. The direction of electric field will be inwards in case of negative charge. Here at the same infinity we are having plus Q naught charge. Now, take a look. I will tell you two things here. First one, if you take 2 points A and B, at which point the electric potential due to this plus Q is more? Here the potential is VA, here the potential is VB, for example. Similarly, here VA, because this point is A, this point is B, therefore here the potential is B. See, in order to bring this positive charge from infinity to B, we have to do small work, because small amount of energy we should spend, isn't it? Because the distance is less, that is from infinity to point B. That is just like, say for example, it is Kashmir, it is Madhya Pradesh and it is Karnataka. Okay, in order to bring, I mean from north to south I am saying, in order to bring an apple, Kashmiri apple from Kashmir to Madhya Pradesh is easy when compared to when we bring that apple from Kashmir to Karnataka. We need more energy, we need to do more work. Since the concept of electric potential is mainly to do with work, more is the work done, more is the potential. Therefore, to bring the charge from infinity to B, we have to do small work compared to this. Therefore, here the potential is less. To bring the same charge from infinity to A, we need to do more work. Therefore, at A, the potential is more. That is, VA is greater than VB. Here also, if you take a negative charge, if you take the negative charge, then this negative charge goes on repelling this negative charge. Therefore, to bring this from infinity to here, we need less amount of work or less amount of energy. To bring this minus Q naught from this point to this point, we need to do more amount of work. Therefore, here the potential is more. Okay, fine. See. Okay, now. So, this is one thing. The second thing is, here I will take the positive charge only. Okay, now. To bring a positive charge from infinity to positive charge is very risky job. It is just like moving north pole of a magnet towards another north pole, isn't it? It becomes very difficult for us. It will go like this, isn't it? But it is just like a south pole and it is north pole. Easily it will come towards the what? Negative charge. Therefore, here we need to do, actually no need to do any work. So otherwise the potential is very less. Here the potential is more because we need to do more work here. Therefore, so actually what we say is potential due to a positive charge is more compared to potential due to a negative charge. Okay, na? Okay. Next, let us discuss about the same type of concept. electric potential difference. Electric potential difference, but we usually represent electric potential difference in terms of delta V, since it is the difference. Okay, let us consider a source charge plus Q, due to which the direction of electric field is outwards and it will extend up to infinity. Why we are taking that infinity means at infinity the both electric field and electric potential will become zero. That is the reason why we always take infinity as a reference. Otherwise, we usually say the potential of an object with respect to Earth. Okay, now, but here for electrical experiments, we used to take infinity as the reference point here. Okay, say for example, the point A, the point B, like this. Now you are in a position to say at which point does the electric potential is more, means at A the potential is more, at B the potential is comparatively less, isn't it? Okay, now here the potential is VA, here the potential is VB. Potential at B due to this positive charge is VB, potential at A due to this positive charge is VA. Now the concept of electric potential difference delta V says that it is the amount of work done to bring a unit positive test charge from one point to another point. Again the same dialogue, that is against field direction. See, electric potential difference in an electric field, I mean electric potential difference between 2 points in an electric field can be defined as the amount of work done in moving or in bringing a unit positive test charge from one point to another point in that electric field. Okay, now see here, now my intention is to bring a unit positive test charge from this point B to A. Now the potential difference will become delta V is equal to, I am doing some amount of work, that is W, charge is Q naught, simply W divided by Q naught I will take. Here the potential is more, therefore I will take more potential minus less potential is equal to W divided by Q naught. Okay, now, so this is how we usually represent electric potential difference. Electric potential difference between 2 points in an electric field can be defined as the amount of work done in moving a unit positive test charge from one point to another point in that electric field. Okay, now next, see, by the method of inspection we can easily say that since in RHS we have W divided by Q naught, the SI unit, the dimensional formula and the properties of electric potential difference are same as that of electric potential, but the definition is different. Similarly, they can also ask you one more question. Define the SI unit of, define the SI unit of electric potential difference. If they ask you like this, what you say? Very simple. We know that the SI unit of electric potential difference is volt. It is said to be 1 volt when 1 joule of work is done to bring plus 1 coulomb of charge from one point to another point, like that. Very simple now. See, when W is equal to 1 joule and Q naught is equal to plus 1 coulomb, then delta V becomes 1 volt. That is, electric potential difference between 2 points in an electric field is said to be 1 volt if 1 joule of work has to be done to move plus 1 coulomb of charge from one point to another point. Like that, we say electric potential difference. Please remember. Okay. Now, I will tell you the alternate method of understanding this positive potential and negative potential. See here. Suppose first one, when we place a positively charged body on the earth, what happens? See, this is earth, this is the body. The body is having positive charge on its surface. When such a body is placed on the surface of earth, we simply represent this as. Now, what you can expect now? Please remember the concept of charging by induction. What it says here, what is the potential of earth? Already I said it is 0 volt. In order to make this surface as 0 volt, it will send electrons. It will send the electrons till the potential of this positively charged body becomes 0. Electrons are flowing like this means the positive charges are coming like this. Positive charges are coming like this means current is coming like this. Please remember, current always flows from high potential to low potential. So just like heat energy always flow from high temperature to low temperature. Similarly, current always flow from high potential to low potential. Already I said the potential of positive is more compared to negative. Okay, anyhow, when compared to this 0, positive is more. Therefore, current flows from body to earth. Similarly, when we place a negatively charged body, on the earth, what happens? Let us take a negatively charged body and let us connect it to the earth. It means we are placing that object on the earth. Now, its potential is 0 volt. Its intention is to make its potential 0. Therefore, what it will do means it will take the electrons from body. Okay, now. So as soon as the electrons get eliminated or get removed from this body means what? It will become neutral. See, it means current will flow from earth to body. Therefore, when compared to negatively charged body, the potential of earth is more. It is obviously true that 0 is greater than negative. Like this, we can understand the concept of electric potential and electric potential difference. Okay, fine. In the next class, let us discuss about one important 5-mark derivation, that is an expression for electric potential at a point due to an isolated positive charge. Okay? Okay. Anyhow, thanks for watching.